So, a valid argument is basically a sequence of premises that lead to a conclusion, and which is based on a tautology, which is to say that the logic behind it is always true. Now, you may be thinking to yourself that you do not want to write down a million truth tables every time you make an argument. And this is a good point. So, writing truth tables is very clunky. So basically what we're going to do instead is find some basic valid arguments and then use those to construct more complicated ones. And these are what we call rules of inference. So, what are our rules of inference? What I want to do is just quickly run through a couple of tables, because basically there are a lot of them, and I do not encourage you to memorize them. So there's a couple big tables, and even these tables don't contain all of the rules of inference that you'll want to use, but I do want to go through them quickly just to give some examples of what kind of basic arguments are totally legit. And I do encourage you, again, not to memorize them, but to keep these tables around so that you can refer to them. So I will probably post, if you have a textbook, they're from the textbook. They are tables 1 and 2 in section 1.6, but I'm going to post them on B courses as well, so you'll have access to them there. So I may ask you at some point to use rules of inference and tell me the name of the rule that you're using. Don't memorize them, just look at the table and then, get the name from there. So the first one, the modus ponens, this guy up here, is the one that we were talking about before. If you know that P is true, and you know that P implies Q, then you can conclude that Q is true. So that's pretty basic. Hopefully it's pretty clear that that's true. A lot of these are pretty basic. There are not many that are very complicated. So let's go to the second one, modus tollens. This is basically what I would call a contrapositive. Or somehow it's the contrapositive of the first one. Which is to say, if you know that P implies Q, and you know that Q is false, you can conclude that P is false. And somehow what you're doing here is you're using the equivalence P implies Q is equivalent to not Q implies not P. So somehow you can use that to put it more in this first situation, where if you know not Q, and you know not Q implies not P, you conclude not P. So I'm going to erase that, but maybe I'll leave this note. The next one, hypothetical syllogism, again is pretty straightforward. If you know that P implies Q and you know that Q implies R, you can just put them together to say that P implies R. So essentially this just means that you can chain these two arrows together. Right. you know, there's very fancy names for these things, but the logic behind it, hopefully, is not much too complicated. Okay, disjunctive syllogism. What is this? So if we know that P or Q is true, and we know that it's not P, then it must be Q. So this is just using the fact that or is true when one of the two things is true. So if one of them is false, you conclude that the other one must be true. The next three, I think, are possibly even more straightforward. Addition is, again, just using the basic property of or. If P is true, then P or Q is true. I mean, this is somehow strictly weaker than this. So it certainly implies that. And similar for simplification, if P and Q is true, then P is true. That's just how AND works. Also, how AND works is conjunction. If P is true and Q is true, then P and Q is true. They're both true. That's how AND works. Finally, resolution, this last one, is potentially a little bit more complicated. And I think it's also possible that it can be used in more complicated ways. But maybe that's worth saying for all of these. So going through the logic to justify them is basically quite simple. But actually putting them to use in practice can be, you may be able to use them cleverly in ways that you don't expect right now. But let's just run through this real fast. If you know P or Q is true, and you know not P or R is true, then you know Q or R is true. And this, again, is not too bad if you just run the possibilities in regards to P, particularly. So P is either true or false. One of these two things is always true, right? Or maybe more importantly, one of them is always false. So if this one's false, then Q is true. And if this one's false, then R is true. So one of these two things, we conclude, has to be true. That is what resolution is saying. And then we move on to table 2, which is rules of inference for quantified statements. These, I would say, are almost even more straightforward than the previous table. They're basically very simple applications of what it means to be one of these quantifiers. So if it's true for all of that, excuse me, getting ahead of myself. If it's true that for all x has some property, then certainly you can find some element with that property. If some property is true for an arbitrary element in your domain, then it is true for all elements in your domain. I mean, this even seems like it's just saying it in slightly different words, but saying exactly the same thing. It may be worth noting that there's maybe some content here in the sense that often this is how you'll make an argument, that if you want to prove something like this, you will choose some element in the domain without specifying what it is, and you'll prove that it has this property. And that's how you'll prove the universal quantifier. And then for the existential quantifier, if there exists an x with some property, then you can find an element with that property. And conversely, if you can find an element with this property, then the existential quantifier is satisfied. So okay, let's dispense with running through all these tables and instead do some examples. So let me get a new page. And take our little example up to the top. So here's a little example that I prepared. I'm trying to keep up with this this habit of using examples from actual real things. So here is a lemma from my thesis. And lemma, if you're not familiar with this word, a lemma just means some fact that is important, but not, a little important fact. So lemma means it is little. So again, I don't really want to go through what this is saying in detail. What I do want to do is highlight how the logic is working. So I have separated it out into pieces, and then I've sort of abstracted away what is being written, and I've just left the logical structures. So what we're trying to prove is that if P and Q, then R. And these are the steps we're using along the way. So what does it mean to check that this is a valid argument? So first of all, let's write down more precisely what we're even saying with this argument. So what does the argument look like in the way that we wrote those other arguments before? So our premises are this and these, and our conclusion is this guy. That's the argument that we want, right? So our argument, let me write it down like this. P and Q, that's a premise. P implies S, Q implies T, S and T imply R, imply U, and U implies R. Therefore, R. So these are our premises, and this is our conclusion. So these we can think of as sort of a hypothesis, or as like outside facts that we are bringing in to perform part of the proof. But in any case, these are things that we are assuming are all true, and then we want to prove that R is true. So how do we check this? We check this by breaking it down into rules of inference. So let's go through this example, and hopefully you will understand what I mean. So here's our argument. So let's start with the first premise, P and Q. So I'm going to write each step and then why we know that that is true. So this is a premise. We're assuming it's true. So I have my book next to me. I am going to be looking in this book for this table because I do not have these things memorized myself. So I know P and Q, and I want to conclude P is true, and I want to conclude Q is true. And so these steps are both called simplification. And it's coming from step one. So let me actually real quickly just look at the table again so that I can make sure everyone understands what I mean by this. Basically, we're using P and Q to conclude P. That's this step, right? And then this step is the same thing with Q. And that is exactly this step, or this rule of inference in our table. If you have P and Q as your premise, you can conclude P by simplification. So that's where I'm getting these things from in the steps that I'm going to be taking. I'm not going to keep referring back to this explicitly, but you should have, you should know that I'm referring to my book next to me. And if you have a table of your own, you can follow along. But again, I will post it on B-Courses. Okay, so let's undo all of this. Okay, so now we know P and Q are true. So far, so good. What do we want to say next? So, next, let's bring in more premises. So P implies S is a premise. And we can use it to conclude S from, this is the thing in the table is called modus ponens. And it's coming from steps 2 and 4. So we know P, and we know that P implies S, so we conclude S. And then a similar process with our next premise. So we know, or we're assuming Q implies T, this is the premise. And we conclude T by the same argument. This time we're using 3 and 6. How did I know to introduce S, T, and U? This is a good question. So let me say that that is beyond what we're talking about today. That's part of the understanding the mathematics and the proof writing. So I'm not worried about what they are and why they're there for now. I'm just worried that the logic makes sense. But so if you're how did we know to introduce S, T, and U? That's basically the content of coming up with this proof is figuring out these intermediate steps that will lead you to the conclusion. So, that's what we'll be doing all semester. But for now, in this particular argument, I'm not worried about that. I'm just worried about checking the basic logical structure. So let's keep going. What do we want to do next? So we've concluded S and T, and we want to use S and T, so let's conclude S and T by conjunction from 5 and 7. Right, since we know S is true and we know T is true, we conclude that S and T is true. Now we can introduce this next premise. And conclude that U is true by this good old thing. if we know this, and we know that it implies that, then we can conclude that. So this one, we're starting to use this a lot. It's a basic rule of inference, so we will be. So this is 8 and 9. And then finally, our last premise, U implies R. Then again, by our good old modus ponens, we conclude R. From 10 and 11. So here is a view of the whole thing. And let me, now that we've written this out, let me take a quick breather and then go over it real quickly again, just to make sure everything makes sense. So what we've done here is I've taken a mathematical argument and I've stripped away all the details of the technicalities of what's going on, and I've only left the structure of the argument. So P is some proposition, Q is some proposition, and R is some proposition, etc., right? This, the argument is using some intermediate steps, which are these things. And we want to check that this is a valid argument in the sense that these premises do indeed imply the conclusion. And the way we do that is by taking the premises and combining them with rules of inference to conclude at the very end what we wanted to conclude. So the fact that you can break this down into rules of inference means that the argument is valid. So one last thing that I want to note is you will often be tempted to make arguments that are not valid, and you should not. So, well, what do I mean by that? So you should watch out for they are called fallacies. So a fallacy is an invalid argument. So you should watch out for common fallacies because they are harder to avoid than you may think. So let's give some examples. These are some common ones. So P implies Q, and Q, therefore P. So this looks, if you're not paying very careful attention, looks a lot like that rule that we kept using again and again, but we switched out the rules of Q and P here, and it matters very much which one you have. So essentially, what you're trying to use here is the converse. And as we said before, this is not the same as that. They are different things. They are not equivalent. So this is a fallacy. Here's another one along similar lines. P implies Q, not P, therefore not Q. Again, this is quite similar in the sense that it looks vaguely like this. It looks vaguely like the modus ponens rule that we keep using, but we're using a slightly different version, which turns out not to work. So this is more like the inverse. Or what you want to use here is the inverse, not P implies not Q, which again, the converse and the inverse are not equivalent to this thing. So these are invalid. Let me quickly say for contrast, if you have an argument P implies Q and not Q, and you conclude P, this is valid because you're using the contrapositive. And remember that it is equivalent. So you can think of equivalences as being very much like rules of inference. Let me say you can use equivalences like rules of inference. Because again, equivalences are founded on logic that is always true. This equivalence means that these things are always the same. So if it works for one, then it works for the other. And I want to say, so first of all, let me answer quickly a question in the chat that I missed at the time. If we go back up to this part where we're breaking down this argument in terms of rules of inference, these numbers and these numbers are the same. So these are referring to the line numbers. Nothing in the table. Yeah, I'm just using the names to refer to the table. All right, what I mean here, so using 2 and 4, what I mean is that if you look at line 2 and line 4, that is what is allowing you to conclude line 5. Okay. So let me just finish by saying, this may or may not be perfectly clear as you're looking at it now, but either way, I assure you it will be much less clear when you are dealing with these things with proper mathematical arguments. So even if it is obvious to you now that this is not a valid argument, you may find yourself making arguments that turn out to be this when it is not as simple as just logic. So let me give another example that is close to my heart. Another fallacy. P implies Q, therefore P if and only if Q. This, I would say, is pretty obviously not true. I mean, this is pretty obviously not a valid argument, but I distinctly remember when I was, myself starting to learn proofs, the first proof-based class that I took, sure enough, I got an assignment back, which was, the task was to prove some statement that was if and only if, and I could not figure out what I did wrong. And I remember looking at it for such a long time and being so confused at checking my argument, and it was fine, there were no problems. Why did this not, why was this not correct? And eventually I found out that I had only proved one direction. So be sure, don't do that. Don't do what Sander did. If you're proving if and only if, what's true is that P implies Q and Q implies P. Therefore, P if and only if Q. This is what you want to be doing. So again, that is just to say that these things may not always be as obvious in the wild as they look right now. But if you learn them now and you pay attention, then that will really help you understand how to make good, solid arguments.